Hello and welcome. Today we are going to be talking about spectra of the elements. So now that you know a little bit about properties of waves and characteristics that we can measure and record about energy, we're going to look at specific relationships of absorbing and releasing energy to individual elements. So we already know a little bit that when energy is absorbed, that pushes electrons out, and as they fall back down, that energy is released. We are then going to use that understanding to identify why elements produce the specific atomic emission spectra that they do. When we think about the interaction of electrons and light, if we would look at white light, it would be considered continuous spectrum. So if you're in the classroom and you look up at the fluorescent lights, what you would see is that all of that white light is actually a combination of different colors. If you use a prism and shine that light through it, it will separate out the colors based on those energy levels. When we look at the movement of electrons, remember we learned that they have to take on that energy in specific amounts. So when we start interacting elements with that continuous spectrum, we're going to see some variations that occur because elements absorb specific amounts of energy. But what we would see if there's no element absorbing or releasing energy would be kind of this blend of all the colors. So this transition from red to orange to yellow to green through violet, and it would be spread out as into the different energy levels. Each element will have its own set of lines that are produced when we run energy through a sample of that element. And there's two different ways we can detect it. We can detect emission lines, the energy that's released when the electrons fall back down. So that's coming from electron fall. And absorption lines would be the energy that is taken out that the electrons absorb to move out. So it just depends on when you do the detecting. So if we shine a light through the sample, the amount of energy that's absorbed would be missing. Okay, so this is the energy that was absorbed, the black line. And the detector would find everything that passed through except for what was absorbed by the atom. This would be the energy coming out. And the detector is picking up specifically what the element is releasing as those electrons fall back down. The pattern comes from how many electrons are in which energy levels, because that determines where they have room to move as the electrons absorb energy. Think of it like fingerprints. All of us have unique fingerprints that identify us. These patterns of emission and absorption, due to the unique arrangement of the electrons in the elements, produce specific and unique spectral patterns. So here we see a few examples. Hydrogen has a very low energy emission over here. Remember, red is on the low energy end. And then we have this kind of green-blue, a more blue, and then several in kind of the blue-violet range. Sodium has two emissions in the visible spectrum. And what we have to remember is some emissions are not visible. So just because we only see emissions of certain patterns doesn't mean it isn't emitting some other amount of energy, but some of them are invisible. They might be in the ultraviolet or in the infrared range or else. But notice how distinctly different these patterns are. So if we had an unknown sample and we wanted to know what elements were in it, if we do a test of their emission spectra, we might be able to identify which elements are present based on the known patterns of emission spectra that exist. Now, when we look at hydrogen, what makes this element unique? And we are going to do the flame test coming up, but we've kind of hinted at the fact that elements produce specific colors. We're seeing that happen as the electrons rise and then fall. Hydrogen has only one proton and one electron. So when we see specific energy released, we know it's due to a single electron moving in a particular pattern. So notice here, if we use a Bohr model to specifically identify each energy level, such as 1, 2, and 3 listed here, when we detect a wave coming off and we sort them by increasing amounts of energy, we can actually identify which rings or energy levels it was moving through. Remember that the energy levels are just the rings are indicating an energy level, but the elements, electrons exist in the cloud. So those kind of three-dimensional shapes you learned about earlier. And again, because there is only one electron per atom in hydrogen, we have much more ability to tie a specific color and energy level to a specific fall of the electron. So that is one of the things we're going to be comparing as we look at the next slide. So if we look at the arrangement of the energy levels, they actually get a little bit closer together the further away from the nucleus you are. So that is being represented by these outer rings being a little closer together than the inner rings. When we look at a hydrogen emission spectrum, the red line is the lowest energy release. So that means it must be a little or a short fall. It's not moving very far. If we look here, as this electron falls from energy level 3 to energy level 2, I've represented that red emission with this wave that I have color-coded red. Notice I stretch that wavelength out a bit to indicate that it is lower energy and lower frequency. When we take a look over here, this purple 410 is a higher energy release. That comes from an energy level 6 to an energy level 2 fall. The bigger the fall, the more energy released. So for hydrogen specifically, we are able to correlate each emission line to a specific transition between the energy levels because there is only one electron moving around. Remember, that is what's key here. Only one electron within the structure of the atom. Because a sample of hydrogen would have many, many atoms, we are seeing all variations of those electron falls at the same time. But because it has only one electron per atom, we can correlate each emitted photon to a specific energy level transition. Once you have elements that have more than one electron within them, then it becomes a little bit more complicated and we are less able to correlate that specifically. But the more electrons you have, the more complex and different your emission spectra will be. So the next steps would be taking a look at your assignment, which will ask you to compare and analyze different emission spectra, make some conclusions about which emissions are high or low energy, and use that to make some conclusions about unknown elements. If you have questions, please make sure you check in with your teacher and make sure you finish your notes section for this part of the notes.